Welcome. We're doing topic 3 in Math 30-2's logarithmic functions unit, and we're going to be looking at solving exponential equations using logarithms. Now, we've already learned 2 methods to solve exponential equations. We've learned to do it algebraically, and we've also learned to do it graphically. And today we're going to learn how we can use logs to help us solve it. Now, an exponential equation is an equation, we know this, that has a variable in the exponent. Adam and Sarah, we're going to explore this, are asked to solve the exponential equation 5 times 4 to the x minus 1 equals 40. And each person uses a different method. So we're going to look at Adam's method first. First, what Adam does is he divides both sides by 5, right? So he divides out the 5. From both sides. Okay. Next, he looks at his 2 terms for his 2 bases, 4 and 8, and he rewrites those into a common base. So he rewrites both 4 and 8 into a common base, because they both can be expressed with a base of 2. 4 is equal to 2 squared and 8 is equal to 2 cubed. Okay. Next, he applies the exponent laws. By looking at his exponents, right? And then in the last step, because they have the same base, he sets the exponents equal and solves for x. Okay. Now, Sarah's method, she's going to use the log method. Now, we've learned that if 2 things are equal, if you take the log of those 2 things, they are also equal. So she did the same thing in the first step. She divided out the 5. Right? And then she logged both sides. Okay. Now she applies her log laws. And she brings the exponent in front. That's right here. Right? She moved it from here to in front. Okay. Then once she's done that, then she uses algebra to solve. Okay, she moves her log 4x over by dividing, and then she divides those out, and she solves. Okay, and what you notice is you get the same answers. Okay, so we can use this as a strategy to help us solve exponential equations. Oops, what? All right, now, Sarah used common logarithms in step 2 of her work. Could she have used logarithms in another way? So, yes. So what she could have done is use the logarithmic form, sorry. Because we have log 4 x to the minus 1 equals log 8, she could write this as log 4 8 equals x minus 1. And then rearrange and solve, right? Log 4/8 equals 1. And this becomes log of 8 divided by log of 4. Not equals 1. Plus 1 equals x. Plus 1 equals x. Log 8 divided by log 4 is 1.5. We could try that out here. Log 8 divided by log 4. Oops. Watch your brackets. So I wasn't paying attention. So it equals 1.5 equals, so 1.5 plus 1 equals 2.5. Okay, so just slightly different methodology, but it does get you the same answer. Okay. In the exponential functions unit, we saw that an exponential equation is an equation that has a variable in an exponent. So this is what I talked about earlier. We learned how to solve graphically. We graph the left-hand side as y1 and the right-hand side as y2, and then find the x value of the intersection as the solution. We also found that you could equate the exponents when the bases are the same and solve. This is an algebraic method. Okay, and now we're learning that we can take the logs of both sides of the equation and solve that way. Now, if the bases cannot be written using a common base, then you can use logs. If the two expressions are equal, then basically, if m equals n, then log of m with base b is equal to log of n with base b. Okay, with those restrictions in place. So if we get a situation, we don't want to do it graphically, we can't make the exponents the same base. What you do is you log both sides, and then you use your log laws to solve. Okay, so we're going to do some examples because examples is how we learn. So here we have, we're going to solve the following exponential equation for this, and we're going to use different methods. We're going to use all three methods. So first one we can do is the change of base, right? 27 is equal to 3 cubed, and we have the other side being 3 already. So we can rewrite 27 as 3 cubed is equal to 3x plus 8. From there, that means 3 is equal to x plus 8. We rearrange to solve for x. So x will equal -5. Okay, that's that one's doable that way. For graphing, we're going to make y1 equal 27, y2 equals 3x plus 8. And so we'll put that in our calculator. So we have 27, 3 to the power of x plus 8. I'm going to change my windows to make sure that y goes big enough. And I'm going to graph. So there's my y is 27, and there's my exponent. Second function, trace. No, second function, trace. I want my intersect. I think I missed a thing, a button there. First curve, yes. Second curve, yes. Guess? You betcha. And I get x equals -5. Y, I get the same answer. Now we're going to do it using logs, right? So using logs, we have 27 is equal to 3x plus 8. So we convert to log form. So this would be log of 3, 27 is equal to x plus 8, right? And from that, we get log of 27 divided by log of 3 equals x plus 8. From that, log of 27 divided by log 3 equals, it's going to look very similar. plus 3 equals x plus 8. And you can do that on your calculator, right? So if we clear this, log of 27 divided by log of 3 gives me 3. Okay, and then I solve for x, which is negative 5. Okay. Now this way I converted to log form. You can also log both sides, and you will get the same equation. Okay. So there's two different ways there you can do it. Okay. Let's do another example, and maybe this one I will do logging both sides. So by logging both sides, I'll get log 20 is equal to log 3 2x minus 1. And then I apply my log laws. I'll get log 20 is equal to 2x minus 1 times log 3. Now I'm going to divide both sides by log 3 to get rid of it on this side. Right? So here we got log of 20 divided by log of 3, and sad to say you're going to get decimals. I'm going to get 2.72, and we'll say 7, is equal to 2x minus 1. I'll move that 1 over, and I'll get 3.727 equals 2x. And then from here, I'm going to divide both sides by 2. So x will equal 3.727 divided by 2. So I'm going to add my 1 and divide by 2. And I'll get x is equal to 1.86 approximately. It doesn't say where to round it, so I'm going to put a 3 there. It's approximate because we're rounding, right? Because this had a continuation. But we got an answer. Ooh, yeah. Okay. So you can use these logs to help you solve the problems. Okay. Let's do this one here. Now let's first start by rearranging. 1, 2, 5, x minus 2 is equal to 5. Now we can put this in logarithmic form, right? So we can put it in the form log 125 of 5 equals x minus 2. So I'm just using that conversion ratio, right? This is the same as log 5 divided by log 125 equals x minus 2. So let's calculate that. Log 5 divided by log 125. And I get, 0.3 repeating. Well, that's the same as 1 divided by 3, right? 1/3. So 1/3 equals x minus 2. So I move the 2 over. It'll be 2 and 1/3 equal x. I'm just going to change the size. I can also rewrite that as 7 over 3. 2 times 3 is 6, plus 1 is 7. So sometimes you log both sides. Sometimes you just put it in logarithmic form and solve. Both ways will get you to your answer. Okay. We can use logarithms to solve half-life problems. Okay. Half-life equation. A is equal to a prime times 1/2, and that represents, the 1/2 represents the fact that we're looking at 1/2 of what we had before, to the power of t over h. T represents the time, and h is the time where only half of the substance remains. So we're going to use logarithms to help us solve a half-life question here. So looking at this problem, let's see what we have. We started with 500 grams, and when we tested it, we only have 13.417 grams remaining. This is of radon. And it has a half-life of 3.8 days. So we want to know how long have they been holding on to it. So we have 13.417. A prime is 500, that's what we started with, times 1/2 to the t over 3.8. Okay, so let's start by dividing both sides by 500 to clear that out of there, right? So 13.417 divided by 500 equals 0.026834. And it cancels out on this side, so we get 1/2 to the t over 3.8. So we can put this in logarithmic form. So it will be log of 1/2 or 0.02634 is equal to t over 3.8.
The pharmacist is not here and set up yet, so we'll do an announcement when they're available. Thank you.
Sorry for that interruption. It is this time, right? Now we want to get rid of that 3.8. So let's multiply both sides by 3.8, right? Okay, so it'll divide out on this side. So I will have t is equal to 3.8. And remember, we can change this log to log of 0.026834 over log of 1/2. Find our log laws, right? And it's times 3.8. So let's put that in. 3.8 times log of 0.026834 divided by log of 1/2, which is 0.5. And I need to close that. I'm sorry about all those brackets. And when we do that, we get 19.835. So that's the time. That means sometime on the 19th day. That's where we're at. So it's, you know, a little bit into that day. Okay. They asked just to the nearest day, right? Is the restriction there, or the rounding rule. Okay. These do take a little practice. The best thing to do is practice with them. Now we're going to do an interest question. This is our formula for interest. Yvonne has a balance of $3,215 in her savings account. It pays at a rate of 2.14 and annually per annum, compounded semi-annually. So make sure we note that, because that's going to affect our formula. A represents future value, P is the principal, and I is the interest rate applied to each compounding period. N represents the number of compounding periods. So it wants to know how long will it take for Yvonne's balance to reach 5,000. First, we've got to figure out our formula. Because it's compounded semi-annually, our interest rate is going to be 2.4% divided by 2, because it's compounded semi-annually, so it'll be 1.2%. And that means too that N equals a half a year, okay, or 6 months. Okay, so when we figure our formula out, we'll have A is equal to, our principal value is 3,215. This is 1.2%, which we can rewrite as 0.12, because we just moved the decimal over, to the N. Okay, now she wants to know how long it's going to take to get $5,000. So that's our goal. First thing I'm going to do is divide out my 3,215. Okay, make it simpler. So 5,000 divided by 3,215 equals 1.555 2, we'll say, times 1.012, or equals 1.012 to the n. So we can put this in logarithmic form. So log of 1.012 of 1.5552 equals n. So this is like log of 1.552 divided by log of 1.012 equals n. So if I do that division, log of 1.55520, I'm going to put the rest of the decimals in because I like them, divided by log of 1.012 bracket, and I get 37.02. And now remember, this is 6-month periods, right? Because that's how many periods. So if I want to know the number of years, I have to divide it by 2. So for number of years, years equals 37.02 divided by 2. So let's divide that by 2, and we'll get 18.5. And it said to the nearest, if we read the question, it said to the nearest tenth of a year. So this is how many years. Okay, so the tricky part in that one was really figuring out the interest rate and figuring out the fact that we're talking about 6-month periods, not years. Okay, so you have to kind of keep that in mind. So here, what we're doing, folks, we are now adding to our repertoire. Not only can we solve these exponential equations by graphing and using algebra, now we can also take the logarithm of both sides of the equation or write it in logarithmic form and use that to solve. That's why we have our log laws. Okay, so you've got to incorporate those in from the other lesson to be able to solve these. Okay, and that's how she wrote.